quarter to 16 in our time. I'm from South Ural State University, which is in Chelyabinsk. Chelyabinsk is situated, it is the capital of South Urals in Russia. It's the middle of Russia, I guess. And our university is rather big. It is the biggest university in South Urals and one of the biggest in the Ural region. Our university was in program which is called 5STO, which is was intended to level up the range of the university. And now we have another program which is called Priority 2030. It is the program of development of our university for 10 years. So we had our first period completed. Now we are making reports. So, but we're doing our research as well. So my topic is optimal control problems for Sobolev type equations. The research of the control problems for mathematical models based on Sobolev type equations is very relevant because we need to study important applied problems such as problems in the theory of filtration, elasticity, biology, and others. And when studying the mathematical models, it is important not only to understand the properties of the processes that we are studying, but also to find the optimal regulation or external influence with the help of which the state of the system can take the required value. So that is why we turned to optimal control problems. And my report is a review of the work of Chelyabinsk Mathematical School under the supervision of Sviridyuk Georgy Anatolyevich. He is my scientific supervisor. So we study optimal control problems for Sobolev type equations with the initial conditions such as Cauchy condition and Sholto-Sidorov condition, or even initial final conditions, and I'll speak about this in my report. So the structure of my report is as follows. First of all, I'll state the problem. Then I present the theory of relatively p-bounded operators. Then I'll speak about strong solutions, which are very useful in solving optimal control problems. And after that, we turn to optimal control problem. And finally, we apply the abstract results to specific Sobolev type models, namely the Barenblatt-Jeltov-Kochina model, the mathematical model of an I-beam buggling, and the Boussinesq-Love model. So first of all, to the linear Sobolev type equations, we refer those non-classical equations of mathematical physics, which can be reduced in suitable spaces to the abstract operator differential equation of the form 1, where the operator A at the highest derivative in time might be non-invertible. So this equation is non-solvable with respect to the highest derivative. When n is equal to 2, there are a lot of, or to 1, it is the first order Sobolev type equation, and there are a lot of works devoted to such equation. We supply this equation 1 with the initial Cauchy condition 2, or the Sholto-Sidorov condition 3, which is most suitable for Sobolev type equations. They are more natural because we don't need to pay attention whether the initial data belongs to the phase space of the equation or not. So we go even further. We consider not only Sholto-Sidorov conditions, but also the initial final conditions for where in the previous Scholte-Sidorov condition, P is the projector on the phase space of the equation. And in condition 4, P in and P fin are also the projectors on the corresponding subspaces of the initial space. Finally, we pose the optimal control problem as finding the minimum point of the specially constructed penalty functional J, and I'll speak about this further. So apparently, Henri Poincaré was the first who studied equations of mathematical physics, non-solvable with respect to the highest derivative. So we speak about end of the 19th century. And the systematical study of such equations started in the middle of the 20th century with the works of Sergei Lvovich Sobolev. So that is why we use this name of our equations, and we say that they are Sobolev type equations. This term was introduced by Ralph Showalter, and it is the synonym to the term of equations non-solvable with respect to the highest derivative, equations of non-Cauchy-Kovalevskaya type, equations of Sobolev type, and so we use the term Sobolev type equations. Here are a lot of works of our, and not only our, school devoted to various problems for Sobolev type equations. The first who began to study controllability problems and optimal control problems for linear Sobolev type equations was Georgy Sviridyuk and his disciple Alexander Yefremov at the end of last century. And these studies formed the basis for a lot of works of our school researchers. We developed theories for optimal control problem for linear Sobolev type equations, as well as optimal control problems for semi-linear and non-linear Sobolev type equations. So let's turn to the theory of p-bounded, relatively p-bounded operators. It is just one of the theories in Sobolev type equations theory. Maybe it is one of the simplest, but when we speak about the higher order Sobolev type equations, it is more complex in comparison to the first order equations. So first of all, we consider two sets, rho A of B and its complementation. Rho A of B is called the relative set, A resolvent set, I'm sorry, of operator B, and sigma A of B is called the A spectrum of operator B. And also we consider these operator functions. The first one, mu A minus B to the power minus 1, which is called the A resolvent of operator B. And the further two, can you see my mouse?
Yes, we can see it.
Okay, this one is called the right A resolvent of operator B, and the left A resolvent of operator B. The operator B is called bounded with respect to operator A, or simply A sigma bounded, if the circle, there exists a finite circle which lies in A spectrum of operator B. If the operator B is A sigma bounded, then we construct operators P and Q, which are projectors in the spaces X and Y respectively. Now we can take into consideration two spaces, X0 and Y0, X1 and Y1. And we can prove the theorem, which is called the splitting theorem, which says that actions of operators split, and also they exist an operator B0, the inverse operator to B0 and the inverse operator to A0. Moreover, we can construct operators H and S, and our A resolvent of operator B can be represented in form 6. So we can also define the infinity as a removable singular point, or a pole of order P, or essentially singular point, according to definition 2. And this also corresponds to the representation of our A resolvent in form 6. If operator B is A sigma bounded and P is a pole of order 0 or natural of A resolvent of operator B, then we call such operator AP bounded, and we use this notation further. Definition 4 defines the classical solution of our initial solution Sobolev type equation. Now consider linear homogeneous Sobolev type equation 1, and further we need the so-called propagator of homogeneous equation to construct the solution of this equation. So the operator function is called a propagator if the function x of t, which is represented in such form for arbitrary v from initial space, is the solution of this equation. And theorem 4 represents the propagators of equation 1 in the following form. Now turn to consideration of non-homogeneous equation, Sobolev type equation 7. Here we need to construct the sets which depend on y, our function in the right-hand side of the equation 7, and it depends on m. These sets we need to solve the Cauchy problem for Sobolev type equation 7. Our initial conditions, our initial functions have to belong to such sets. So theorem 3 is the theorem of existence of unique classical solution to the Cauchy problem for inhomogeneous equation 7. And we have the representation of this solution in form 9. Here, as you can see, we use the propagators that were constructed for homogeneous equation. And since our equation 7 is Sobolev type equation, it is not degenerate, we have this sum which corresponds to the solution which is defined on the kernel of the on the kernel of the projector P, which was constructed earlier. After that, we also can prove the following theorems, which say about the solvability of the Showalter-Sidorov problem and initial final problem for the Sobolev type equation. So theorem 4 says that if we speak about Showalter-Sidorov problem for inhomogeneous equation 7, our initial values can be taken arbitrarily from the initial space X in comparison to the Cauchy problem when we consider the Cauchy problem for the equation. And now let's speak about initial final problem for the Sobolev type equations. Here we construct the projectors that I mentioned before, the projector P-fin and the projector P-in, using our projector P, which was constructed earlier. And if the operator B is AP bounded, then the following operators are projectors, as I said. And we can also construct the propagators of equation in the following form: the propagators of homogeneous equation, Sobolev type equation. And finally, we can formulate the theorem of unique solvability of initial final problem. And here we say that under the following conditions, there exists a unique classical solution to the initial final problem for non-homogeneous Sobolev type equation. And it is given by formula 10. When we speak about optimal control problems, we need to move from classical solutions to the strong solution of such problem, which allows us to set the optimal control problem and use the technique of Hilbert spaces in its research. So further, we define the strong solution of Sobolev type equation. It is the vector function x of this type, and it is called the solution, a strong solution to equation 7 if it turns the equality to an identity almost everywhere on an interval J. And then we can define a strong solution of the Cauchy problem, Showalter-Sidorov problem, and the initial final problem correspondingly. Since we have the following enclosure, I don't know how to say it in this, since we have this
inclusion.
Inclusion, yeah, I forgot the word.
Yeah,
Thank
yeah,
you. Thank you very much. We proved the theorem 6, which says that if the operator B is AP bounded, I'm sorry. Is it okay? If the operator B is AP bounded for some P, then for arbitrary initial data belonging to the following sets that were constructed earlier, there exists a unique strong solution to the Cauchy problem 2.7. And also we have the following theorem and corollary for the existence of unique strong solution to the initial final problem and Showalter-Sidorov problem. Now we can turn to the investigation of optimal control problem. As I said, here we search not only the state of our process, not only X, but also the control U. So we search the pair X and U with hat, which are called a solution to the optimal control problem. If relation 5, which is the minimization of the penalty functional, is satisfied and all the pairs X and U are solutions of problem 1, 2. And in this case, the vector function U with a hat is called an optimal control of solutions to 1, 2. And this is the form of penalty functional which is used in this problem. So we construct the space of controls like this. And it was proved that if the operator B is AP bounded, then for arbitrary initial data belonging to X and Y belonging to the space HP plus N of Y, there exists a unique optimal control of solutions to Showalter-Sidorov problem for Sobolev type equation 1. if the operator, and the following theorems say about the optimal control problem for initial final problem, and also about unique solvability of this problem with Showalter-Sidorov condition. Now we can apply these abstract results to the models that I mentioned before. First of them is the Barenblad-Zheltov-Kochina model. It simulates the process of fluid filtration in fractured porous medium. Here, alpha and lambda characterize the properties of the medium. Parameter alpha and parameter lambda can take any values, real values, even negative. So these values do not contradict the physical meaning of the problem. So our equation 13, which is called Barenblad-Zheltov-Kochina equation, can be degenerate for some values of lambda. Here you place the role of external influence, and it characterizes the sources or drains of the fluid. And so we consider the Barenblad-Zheltov-Kochina equation 13, define the spaces x, y, and u by formulas 14. In these spaces, we can define operators A, B, and C, which were mentioned before. We can construct our resolvent operator like this with formula 16. Since our equation can be degenerate, we can construct the A spectrum of operator P, which consists of such points for lambda non-equal to lambda k, where lambda k are the eigenvalues of the Laplace operator with condition 12, Dirichlet condition 12. So the operator B defined by formula 15 is A0 bounded. We proved that. And we can construct the set, just one set for M equal to 0, because we have first order Sobolev type equation. My has the form defined by this formula. And also we can construct the space of controls of functions U that are figurating in this equation. So for any Y belonging to the space H1 and X0 belonging to the set My that was constructed on the previous slide, there exists a unique solution. We speak about strong solution because further we speak about optimal control problem. So there exists a unique strong solution to the optimal control problem for mathematical model, Barenblad-Zheltov-Kochina model with initial Cauchy condition that minimizes the functional L11. Here I made a remark about the description of this mathematical model again, that it reflects the pressure of the liquid fluid that is filtrating in the porous medium. Now we can turn to the next mathematical model. This model is called the Hopf model on graph. If we consider G, which is a finite connected oriented graph, B is the set of vertices and E is the set of edges. On each edge we consider the Hopf equations 20, and in each vertex we consider the conditions 18 and 19. These are continuity conditions and flow balance conditions. This mathematical model describes the dynamics of deformation of the construction made of I-beams under constant load. Here parameters alpha J characterize the beam material properties, and this term, free term Uj, corresponds to the external load on the jth edge of the graph. So we can reduce this mathematical model to the Sobolev type equations. For this purpose, we introduce the space L2 of G and define the spaces that are used for our model X, like this, with the norm defined by this formula. Then we can define operators L and A using this operator L, and operator B and operator C. Also, we can construct the A spectrum of operator B, and we can prove the following lemma. The operator B defined on this slide for this model is A0 bounded if one of the following conditions hold. If kernel of operator A is 0, so we have non-degenerate case, or we have the following case when the kernel is non-trivial and alpha j are not 0 for any j. So now we turn to consideration of initial final problem. For this purpose, we represent a spectrum of operator B as union of two parts, sigma A in and sigma A fin. They do not intersect, and we can consider initial conditions and final conditions. So one projection of the solution is defined in the initial point of time, and another part of our solution is defined in the final point. Now we can construct the space of controls, and the whole model, Hoff model on graph, is now reduced to the initial final problem for the Sobolev type equation of first order. We proved that for any y, lambda and alpha j, satisfying conditions of previous lemma, for arbitrary initial and final data belonging to the space X, there exists a unique solution of optimal control problem for the Hoff mathematical model on graph with initial final conditions 22. And this optimal control minimizes the penalty functional that was defined by formula 11. Those two models that were presented before, they were first order Sobolev type equations because they had only the first derivative in time. And now we consider the Boussinesq-Love mathematical model, which is reduced to the Sobolev type equation of the second order. And we can use the results of our theory for higher order Sobolev type equations. So we consider the Boussinesq-Love mathematical model, which is based on Boussinesq-Love equation 23. Boussinesq-Love mathematical model describes the propagation of waves in shallow water when the domain omega belongs to R2. Parameters lambda, beta, lambda prime relate to depth, gravitational constant, and bond number. The function x determines the wave height at time t at the point S, and U is a control that defines external forces. So we reduce the Boussinesq-Loew mathematical model to the Sobolev type equation of the second order. For this purpose, we define the spaces X, Y, U, and the operators by the following formulas. Our a resolvent of operator B for the second order equation is defined like this by formula 24. And the A spectrum of operator B is defined by formula 25. We proved that the operator B in such case is A0 bounded, and we also can construct the projector P, which is used to split the spaces that are used in this problem. Now we can pose the Showalter-Sidorov conditions 26. We have two conditions because we have the second order Sobolev type equation, and also define the space of controls in this way. So here n is equal to 2 and p is equal to 0. That is why we have H2 of u. In this space, we single out the subset U at, the set of admissible controls, which is used when we minimize our control, our penalty functional. And we proved the theorem which says about the existence of a unique solution to the optimal control problem for the Boussinesq-Loew mathematical model with Showalter conditions 26. So this is it. Thank you for your attention. If you have any questions, I am ready to answer.
Thank you.
Thank you.
So, there are any